Okay, I think we can continue. So let me, before moving to supersymmetry, let me discuss some of the properties of these micro black holes that I've started the discussion about. So, and then there were some questions here to explain. So let me start first with the properties of big classical black holes. Okay. So as we said from the beginning, so the big classical black holes are objects that are strongly gravitating with the Schwarzschild radius, the horizon, defined in this way. Okay, and we explained in the first lecture the physical meaning of this. This is the well, you can even think in terms of Newtonian approximation that this is the place where the escape velocity exceeds the speed of light. So classically, black holes are absolutely black. Okay, so they cannot radiate anything. The horizon can only grow. They can only swallow things, accrete things, and become bigger. They cannot shrink. Classically, there is no reverse process. The black holes cannot shrink. The horizons can only grow. So classically also, black holes, they have the so-called property of no hair. So sometimes it's called no hair. This means that they don't have hair. What it means, okay? This means that a given black hole, if I have a black hole, I can only characterize it, okay? I don't know, it has to be black, but anyway. I can only characterize it with a very limited number of parameters, of quantum numbers. So the example are the mass, spin, or orbital momentum, and electric charge, okay? Or the magnetic charge, if they have one, or any other quantum number which is associated with a massless gauge field, okay? So in other words, the only quantum numbers which are associated with fluxes that you can measure at infinity, okay? So for instance, we discussed Gauss's law, right, in the previous lecture. So gravitational flux is certainly an example of flux that you can measure at infinity by Gaussian integral, by the Gauss's law. Electric flux, again, is a flux which you can measure at infinity, and so on, okay? So if there is a new, for instance, exotic charge, which we have not discovered yet, black holes could carry that also, as long as you can measure that at infinity, or you or somebody else could measure it at infinity. So in other words, this is the limit. So these are the limiting properties. These are the limited number of quantum numbers that you can use to identify a given black hole. Okay. So black holes have no other identity classically. So for instance, let's consider black holes which have spin 0 and no charge. Okay, just the mass. So what it means that they have no hair. The meaning of this statement, for instance, you can understand it on the following example. You can take a given object, which is electrically neutral, and you can collapse it into a black hole, okay? You can take an object and shrink it down to its Schwarzschild radius once it crosses the Schwarzschild radius. So let's do this. So let's say I have an object. I have an, I don't know, arbitrary object, okay, of some mass m, electrically neutral. Then I have a corresponding Schwarzschild radius. I can find it, right, which is 2 times g Newton times mass. I take mass multiplied by g Newton, okay, twice. I derive the Schwarzschild radius. And then I draw an imaginary sphere. Let's draw it with a imaginary Schwarzschild sphere, okay, inside it, okay. Now, as long as this object is bigger than its Schwarzschild radius, this imaginary Schwarzschild sphere, You can ascribe different types of identities to this object, okay? Which you can measure on a finite time scale, some of those you can measure on infinite time scales, okay? I don't know, you can talk about its shape, color, whatever, quantum number, baryon number, lepton number, different things, okay? Now, if we take this object, this, let's say some dust or something, and we collapse it into a black hole, meaning that it crosses the Schwarzschild sphere. After it crosses the Schwarzschild sphere, after a certain finite time, all the memory about its origin is lost, okay? So end result is a black object, okay? So the end result of this, classically, okay, is a black object of this Schwarzschild radius, and the only memory is the mass, as long as there are no charge and it doesn't have a spin, okay? So only memory is mass. So in other words, the same black hole you would obtain by collapsing, I don't know, a computer with a humongous amount of information or anything else with the same mass, okay? So that's why we say the black holes, they have no hair, because they don't have memory. There is no identity that you can ascribe them other than these very limited numbers, okay? So, and usually when we talk about black holeness, about the big black holes, this is what we have in mind. It's always, this is an intrinsic property of black holes, that they have no memory, okay? Now, if black hole had a memory, then you could ascribe a label to it, okay? So for instance, if I could say that, okay, let's say I collide D plus E minus at humongous energies and I form a big classical black hole. And imagine somehow, although the total electric charge is 0, somehow this black hole remembers the flavor of the electron. So this black hole remembers that it came from electrons and not from muons, okay? Then you could prescribe it, then you could ascribe a label to this black hole, some other number, okay? And then you could distinguish them by this number. The point is that this is impossible. Unless this number corresponds to something that you can measure at infinity, so you need hair to measure at infinity, this black hole has no other identity. For instance, the other day we considered this example, what happens when you take a neutral black hole and you throw an electron inside. Of course, in that case, or electron or any other charged particle, black hole acquires a charge. And you can ascribe this identity, the charge, to a black hole. Now, why? Because you can measure charge at infinity, okay? So this is the essence of this no here. So in other words, it turns out that any other charges which are associated, for instance, with massive fields, for instance, W and Z bosons, okay, they are lost forever, okay? If you throw anything that is charged under weak SO2, massive gauge fields, that charge is lost forever. So you can never recover classically, okay? Okay, so now this is as far as this classical property is concerned of a black hole. Now, quantum mechanically, black holes can evaporate, okay? There is the so-called Hawking radiation. So if you have a black hole of size of radius Rg, okay, there is a corresponding temperature associated with this black hole, okay? And this so-called Hawking radiation. And well, you can even make a guess, right? Intuitively, you can understand that since the only parameter that you see for the black hole, the only parameter is the Schwarzschild radius, the horizon, you can think about the temperature being inversely proportional to the horizon. In fact, it is. You can derive it rigorously. So the temperature of a black hole is inverse Schwarzschild radius. So black holes, they radiate as perfect quantum emitters, okay? Meaning that they radiate in thermal spectrum. So they radiate as a body of temperature T. And the interesting property here is that what this relation tells you, that bigger they are colder, okay? So in other words, very big astrophysical black holes, they are very cold. They're so cold that actually their temperature is negligible. There's no chance ever detecting the Hawking radiation from them. But if you have enough time to wait, and you wait, okay, black holes evaporate, and they evaporate, and of course they lose mass because they evaporate, energy is conserved, which means that since they lose mass, they have to shrink. So quantum mechanically, black holes, they can shrink. So their radius decreases. But you see what is happening is that because their radius decreases, they become hotter. Now, hotter they become, they evaporate more efficiently. And then there is a connection. So eventually what happens is that eventually these black holes, they reach a certain size of your fundamental scale. So in GR, this scale would be L Planck, okay? In these theories that we considered, generically this would be L star. And after that, black holes stop to be anything that you can think in terms of classical or quasi-classical physics. They become quantum objects, okay? So in other words, the point is that once black hole becomes Planckian, there is no really there is no difference, there is no clear difference how you can distinguish that object from an elementary particle of the same mass. Because the Planck scale or this scale is precisely the boundary where you stop, where particle nature, elementary particle nature, and classical black hole nature, they merge, okay? So this is a really transitional period, transitional interval, okay? So black holes evaporate. Now the thing is that, what this will tell us about black holes that we shall, according to these theories, are predicted in high energy collisions, okay? This tells us that, first of all, again, as we said, right, in the particle collisions around, if the fundamental gravity scale is TV, is around TV, in the center of mass energy and impact parameter collisions with that scale, we should start seeing production of first objects, which we can later call black holes, okay? The first strongly gravitating objects. Now, of course, if we had enough energy in the collision, eventually, at very high energy, you start producing something big and classical, okay? But on threshold, where the first black hole start, where you can see first black hole, so in Einstein's theory, this will be Planck scale, okay? At the Planck scale. They, as I said, they are something in between. They are not really real classical black holes. They are we can call them quantum black holes, which means that they are like elementary particles. And indeed, distinction between them and the elementary particles is very blurry. I mean, it's not very clear. Why? Because you see that once the Schwarzschild radius of a black hole reaches the critical scale, okay? So for instance, for Einsteinian black hole, what happens? For Einsteinian black hole, when Rg becomes Planck scale, okay, means that the mass of the black hole divided by m Planck square is the Planck length. This implies that actually the mass of this black hole is Planckian, okay? So in other words, for instance, for a black hole of size, Planck size, the mass in Einstein's theory, the mass is also Planckian, which means that the Compton wavelength and the Schwarzschild radius, they coincide, okay? They are of the same order. Correspondingly, the temperature of this black hole, okay, is also Planckian. If I evaluate naively this expression, the temperature of this black hole is also Planckian, okay? And as a matter of fact, the decay rate, if I evaluate the decay rate according to this quasi-classical prescription, the decay rate gamma will be Planckian, okay? So everything is Planckian. So, which means that this black hole decays pretty rapidly, okay? And effectively, there is no way to really tell the difference between this black hole from the point of view of experimental physics and a new resonance which decays very rapidly with Planck scale mass and decays within Planck time, okay? So this property is identical also in the class of theories in which the fundamental scale is larger than the Planck mass. This property is unchanged, so it's the same story. So if we have black hole production at around TV energies, so what we will see is that first, black holes that will be produced, they will look like, for all the practical purposes, they would look like resonances, okay, that will decay, okay, and like elementary particles, and would be very hard to tell the difference. Okay, so now how can we tell the difference? So coming back to this hair, let's first ask the question, what happens with the hair of a black hole, okay, when the size approaches the fundamental scale, okay? Now, for instance, let's take an example. Imagine you have a theory in which you have many particles. Let's take even standard model, doesn't matter. So we have a bunch of states in the standard model, more than 100, okay? So now, let's do the following thought experiment, okay? So imagine that you are colliding E plus, E minus, and you are forming a black hole, okay? And suppose I give you unlimited energy in the collision, okay? So you can collide E plus, E minus with the center of mass energy of the solar mass, okay? Or I don't know, or the galactic mass, whatever you want. So then the outcome is a black hole of the solar mass black hole, okay? Big macroscopic object, 3 kilometer, okay? So you will produce a big macroscopic black hole of 3 kilometer size. And this object is extremely it's a well-classical object, okay? Quasi-classical. So it evaporates with usual Hawking evaporation. And it evaporates very slowly, okay? It has a humongous lifetime and very low temperature, okay? Now, what will happen is that this black hole, after a certain finite time, so this is the picture, right? So we collided this, we formed a black hole, okay? And then this black hole evaporates, but it will evaporate completely democratically and thermally in all the available states. So, meaning that at the beginning, when its temperature is very small, it will mostly evaporate into graviton, a photon, and if there are other hypothetical massless particles, it will also evaporate into those. Then, gradually, after a very long time, the horizon will shrink sufficiently to start evaporating other states. So first, let's say horizon will shrink down to 1 millimeter, and this is approximately 1 millimeter, or whatever, microns. And this black hole at that point will start evaporating neutrinos, okay? So it crosses this threshold of the neutrino mass, starts evaporating neutrinos. Then it becomes hotter, okay? Eventually it starts evaporating electrons. Then it becomes as hot as muon, starts evaporating muons. Now, you see, once it becomes as hot as muon, it will start producing muons and electrons completely democratically, okay? Because it cannot distinguish among these species. Then it eventually crosses over, reaches the temperature of tau lepton, of other quarks. So basically, the story will be that it will, once the temperature is available, everybody that has mass below the temperature, okay, will be produced in a completely democratic way in this evaporation process. Why? Because of this precisely no here point. That this guy has no memory about its origin. And so it's just thermal and completely democratic. All the memory has been erased. So this is a property of the big classical black holes. But the point is that, of course, energies available at LHC are not that high. At best, if we are super lucky, we will start producing a bottom of this tower of black holes. The first state, whose mass is comparable to its Compton wavelength and to its Schwarzschild radius, okay? So everything is comparable. Now, that kind of object, so let's discuss this, right, in a bit more detail. Now, the point is this, right? Suppose I collide a given particle, I don't know, given flavor, and I produce a black hole, okay? On threshold. So in other words, I'm producing a guy whose all the parameters are the same. So mass of a black hole, is of order m star, which is, of course, inverse L star, and the Schwarzschild radius of this black hole RG is L star. So everything is of the same order, okay? And the Hawking temperature of this object is also same m star, okay? So it's approximately, it's T is also m star. So what happens now? So let's say this guy was produced in the collision of a given flavor. I don't know, take a given state. I don't know, whatever you want. Let's take E plus E minus. Of course, this will not be LHC, but anyway, it doesn't matter. So E plus E minus produces this. Then the question is, can this guy decay democratically into everybody or not? And the point is, no, he cannot. Why? Because first, it was produced. So let's do this experiment in the following way. Let's say I collide E plus E minus, and I just choose everything to be of the same order. Impact parameter, energy, mass of the center of mass energy, everything. So there is one scale in the problem. Production rate of this object, whatever you want to call it, let's call it a quantum black hole. Production rate of this object is, of course, again, is also m star. And the decay rate of this object is also m star. But simply by unitarity and CPT, it has to decay by this rate, the same rate, to this flavor that it came from, okay? Which means that it cannot afford to decay into everybody democratically, right? Because the rate is limited. In other words, the lifetime is limited. So this guy has a very limited lifetime, and within this very limited lifetime, this guy has to decide where to decay. But by unitarity and CPT, it has to decay with the same probability into the species of its origin. So therefore, it cannot decay into everybody democratically. It cannot afford to be so democratic, okay? And so therefore, inevitably, it follows that this guy will have a memory about its origin, which is absolutely natural because the memory is there because the lifetime is very short. So this guy has no time to forget. So it has to decay before it forgets about its origin. Okay. So therefore, that's why these black holes, they will carry hair, and because in other words, they carry hair. I don't know whatever you want to call it. They carry hair in the sense that they remember their origin. Okay, before they evaporate, and that's why they will practically look like particles. So will not be nothing like that. You produce this guy, and this guy will sit there and very slowly decay into everybody it can. No, it will decay mostly in a given particle species, most likely in two particles. So probably at LHC it will decay into two jets. And so now, why is this important? This is important because this tells you that if you probe the bottom of this tower, of this black hole tower, there will be practically no way, if you're just looking at that point, practically it will be very hard to distinguish this between any new resonance, okay, which could be there and decay again into two particles or whatever, okay? So now, how can you see the difference? However, you will see the difference if you are able to go above the threshold, above this energy. Why? Because once you go above the energy, what happens is that there is a gradual transition. These black hole properties, they gradually set in. Okay? So bigger is the energy, bigger is this black hole that you produce, it becomes slightly more classical. So once it becomes slightly more classical, it has less memory, it becomes more democratic, but also it has lower temperature, which means that the decay products, they will be softer. The momenta of the decay products will be softer. Now, this is a very characteristic property of black hole physics. That what they do, they absorb hard momenta, they recycle, and then they release soft stuff. Okay, they are like, I don't know what, sponge or whatever. Okay, and this is very different from any other particle type new physics that you could see at that scale. Because you see, let's compare. Let's imagine that we have some. Let's compare this property with the production of a new particle state, okay, around those energies. So if I have a new particle, like, I don't know, W boson, for instance, right? So W plus minus or whatever, right? So at threshold, I produce this particle, it decays back to whatever, the standard model particles or to whoever it couples, okay? Now, once I go above the threshold, I increase energy in the collision, I will become it even harder. I pass this threshold, and again, it continues. Typically, the interaction products are also hard. If collision is at very high energies and you have high momentum transfer, yeah, you see harder stuff. But with black holes, no, because with harder energies, they become fatter, okay? Instead of producing very energetic, few energetic things, you produce many things, but they are softer, okay? And this is a very typical property of black hole physics. And actually, I don't know any analog in particle physics, in quantum in physics in which new physics is elementary, point-like quantum particles. Okay. So this is a very important property to recognize the black holeness of new physics. Okay. Now, on top of this, there will be, of course, now this is model independent because this simply follows from the fact that you are making gravity strong at that scale. Okay. Now, then, of course, will be model dependent properties, which depend on how you are making gravity strong at that scale. If this is the extra dimensions, like what we discussed, if this is because of extra dimensions, then, of course, in those class of theories in which gravity becomes strong because of extra dimensions, there are also different types of predictions, like seeing Kaluza-Klein resonances in the particle collisions. So, for instance, there were these questions the other day. You can ask me more in the discussion session. So you can see Kaluza-Klein. But those are, of course, some of those are model dependent because it depends how the standard model lives in these extra dimensions, how many extra dimensions the standard model gauge group can see in UV at high energies. How are they compactified? What is their size, etc. Okay, so there is all possible exotica, and some of the signatures are very spectacular. On top of this, again, since gravity is getting strong at around TV scale, so you have to say something about the quantum theory of gravity, and in string theory, again. In addition, there will be, of course, production of string states, string vibrations, because once you make classical gravity strong, you have to UV complete theory. You have to complete it with a more powerful quantum theory of gravity. Now, in case of string theory, since we don't have any other reasonably established candidate, there will be spectacular, again, the signatures are pretty spectacular. Of course, you have to be lucky and get to those energies, but what you should see is a production of string resonances, okay? Now, I will come back to this if I have time, but let me just briefly mention that according to string theory, the way string theory incorporates different particles that we see around us is identifying them with different vibrations of a fundamental string, okay? So in other words, the story is that like you have a string of the violin, you can play on the violin, you see different harmonics, right? So exactly in the same way, string theory, mathematically we call it string quantization, okay? Now, so effectively this is like listening to string harmonics. And these different string harmonics, they are literally different particles around us, okay? And by the way, in some pictures are pretty interesting. So let me just mention this for 5 minutes. So suppose, okay, let's say suppose it's I don't know, it's raining outside and you have nothing to do, and you want to write down string theory. Well, just for fun, okay? So, what do you do? So you want to write down a theory of a fundamental object. But then, the moment you want to write down, you say, okay, but strings may be closed, but they can also be open. All right? Okay, then you press on, and then you discover, after some work, that at least in some incarnations, the mathematical consistency of the theory forces you that the open strings, they cannot move freely. Well, then you discover the space has to have larger dimensions, otherwise you cannot formulate theory in a sensible way. So let's, in particular, let's take 10. In some incarnations, it's 10. So let's say you are in 10-dimensional space, and you have this fundamental object, string, moving around in this 10-dimensional space. And then you discover that by mathematical consistency, some of the open strings, they cannot move freely throughout the whole space. Actually, because they have legs, their legs have to be attached to surfaces. Okay? Now, these surfaces have names. They are called D-branes. D-branes. Okay? So D-branes are literally, like, you can think of them as walls or surfaces, okay, which can have different dimensionality. And just like in this way, if think about this two-dimensional surface, okay? So this two-dimensional surface, you can think of it as a D-brane in this three-dimensional space. Now, two-dimensional surface always has certain excitations, which only live on the surface, right? Because if I shake it, there will be sound waves propagating in it, right? So if I shake this thing, I imagine it's infinite, okay? So there will be sound waves running up and down the surface. So these sound waves are excitations of these open strings which are attached to these D-branes. So in other words, the rule is that because they have legs, these legs cannot terminate nowhere. They can only terminate on a specific surface. The way you can think about it, remember I mentioned about this flux, okay? It's very useful to think in terms of flux. So think in the following way, think that there is a flux tube. So think of the string as a flux tube, which supports certain flux, right? So of course, if it's a flux, the flux, as we said, flux lines cannot break. So they can only terminate on a surface on which flux can spread. So the way you can think about it is like this. Like imagine I have a D-brane and I have a flux. So I have a flux line, okay? I have a flux flowing through it, this line. And then this flux spreads on the surface, all right? So that's basically the picture. Anyway, the cool part is that, for instance, in those incarnations, what happens is that, so then you can ask the following question, okay, now suppose I want to understand what are the harmonics of these strings, okay? The strings can vibrate and these different harmonics correspond to different particles. So then you can say, okay, what are these particles that I will discover? And the interesting fact is actually that if you go ahead and quantize closed strings, if you quantize open strings, okay? In other words, if we listen to the harmonics of these open strings, you can get particles of spin 0, spin half, spin 1. I mean, I'm talking about the massless spectrum, the light spectrum. You can never get particles of spin 2, elementary particles of spin 2, okay? So which tells you that from closed string, you can get everything that standard model needs, but you cannot get gravity. On the other hand, from closed strings, you get gravity. You get GR as the lowest lying excitation. And this is interesting because this tells you, this is sort of the string theoretic way to understand why gravity goes everywhere and why you cannot confine gravity to a surface. Because in the string theory language, because these are closed strings, they don't have legs, so they cannot be stuck anywhere. They move freely in the space. Of course, in the GR, it's a geometric language. We understand that gravity is a part of geometry. You cannot have space without gravity. It doesn't make any sense because graviton, as we said, it couples to anything that has energy and momentum, right? Which means that if there is a space to which graviton cannot go, then nothing can go there. Because you cannot send there anything that has either energy or momentum, which means that you cannot send there anything that you can call an object or a signal or a particle. So, and this is the string theoretic way of understanding this, okay? Anyway, so in these incarnations, there will be, of course, the predictions will be that, and people are studying this extensively, that you will see string theoretic recurrences of ordinary particles. So for instance, So they have certain specific spectrum. Unfortunately, I don't have time to discuss this. It's so-called Regge trajectories. And the interesting thing is that so what is the prediction is that for instance, standard model particles, they should have brothers and sisters, which correspond to high excitations of the open string, okay, which will carry, however, higher spin. So, for instance, you can have a spin, or you can have particles which look like gluons from the point of view of internal quantum numbers, but they carry higher spin. So, for instance, spin 2 gluon, etc. And the consequences are pretty spectacular. So, of course, I mean, if you see a higher spin gluon, this will be a very strong evidence for stringy nature of whatever underlying physics is there. Okay. Now, unfortunately, I have to finish this discussion here, and I have, I think, what do I have? I have 5 minutes, right? Okay. I should start, switch to the different things, okay? And then we have another lecture tomorrow, right? The last lecture. So, so I want to discuss, so now let me switch to supersymmetry now, okay? So the way we can arrive to supersymmetry, so let me discuss. This is supersymmetry, okay? So the way we can arrive to supersymmetry, to the concept of supersymmetry, you can arrive in I will not follow the historic route. So we can arrive in different ways. Since we are motivated by the hierarchy problem, okay, we can arrive to the concept of supersymmetry precisely from the side of the hierarchy problem, okay? Then we do it in a different way. So suppose you have a theory. Let's take a very simple theory, okay, which exhibits the hierarchy problem. Now, as we said, hierarchy problem is the problem because the mass of a scalar is quadratically sensitive to the gravitational cutoff of the theory, okay? So suppose you have a theory of a scalar. So let's say I have a scalar, and this scalar is, let's take a simplest possible theory of an interacting scalar. Let me take it complex for simplicity. So I will take this type of interaction. And it has a certain interaction parameter. Let me call it lambda square, this parameter, okay? So, in other words, in this theory, there is a vertex. So, phi for a vertex, okay? And the strength is set by lambda square, okay? Now, I start with this theory with a massless scalar, okay? Now, quantum mechanically, as we said, once we take into account perturbative corrections from virtual particles, okay, the mass of this object, of this particle, becomes quadratically sensitive to the size of your black box, to the inverse size of your black box. So, for instance, here in this theory, there is only one interaction vertex to start with. And so the diagram, the diagram that will give you quadratic divergence into the Higgs mass, so let's call it a Higgs, this particle, okay, will be this. So in other words, this will tell you that there is a mass of phi which is sensitive quadratically to the size of your black box, okay, lambda, capital lambda, to the inverse size of your black box, okay? And so then you take into account gravity, then you realize that once you go above the Planck scale, this guy will become a black hole, so it doesn't make sense to go above the Planck scale in this diagram, and so you end up with the hierarchy problem, okay? So now you can ask the following question: can I introduce a new physics, some physics, which would shut off this divergence, let's say around the TV scale, okay, in the Higgs mass? And after some experimenting around with different particles, you discover that there is a simple way to do it, actually. If you postulate that your theory also contains a fermion, which is also massless, okay, and has an interaction which is set by the same parameter lambda, okay? So in other words, if I take this term in the Lagrangian, and if I introduce a fermion, let me call it psi, and I add the interaction term between phi and psi, then it turns out that in that case, the quadratic divergence gets cancelled, okay? Why? Because on top of this diagram, where phi is running in the loop, there will be another diagram in which, again, phi is external, but now psi is running in the loop. Now, both diagrams go as lambda square, because here I have lambda here and lambda here. And the signs are opposite because of the spin of a particle which is running in the loop. And so it turns out that in this case, the answer is simply 0. Okay? There is no quadratic divergence. There is logarithmic renormalization of the kinetic term, of course, the wave function renormalization. But there is no quadratic sensitivity to the cutoff. So then, okay, so then you get a bit surprised. You say, okay, but what is going on? Something there should be a reason for this, okay? That there is a cancellation. I mean, as you know very well in physics, usually things do not happen without reason. If there is somebody light at a scale where this somebody is not supposed to be, then there is a reason for it. So for instance, pions are light because they are Goldstone bosons, pseudo-Goldstone bosons. Okay? So there is some physics behind it. So here, this guy is light. It's light because of symmetry. Okay? It turns out that in this theory, there is a symmetry, which we'll discuss in a second, which relates this fermion this scalar and the fermion to each other. Now, as we said, once you have a symmetry which relates scalar and the fermion, okay, which means that once there is a symmetry, the symmetry tells you that the mass of the scalar should be tied to the mass of a fermion. Then you know that this scalar is safe. Why? Because fermions, they have their own symmetry, which protects them against quadratic sensitivity of their mass to the inverse size of a black box. This is the chiral symmetry, right? Remember, we discussed this briefly, that the mass of a fermion is always a transition between a fermion of left chirality and the right chirality, okay? When mass goes to 0, chirality becomes a good number, good quantum number. In other words, when mass goes to 0, there is a symmetry in which you can rotate left fermion and right fermion with completely independent phases, okay? And because of this, this is what guarantees that the fermion mass is not quadratically or any other, is not power law sensitive to the cutoff, but is only logarithmically sensitive. Why? Because the point is that if you set this mass to 0, it should not get renormalized because of chiral symmetry, okay? I don't want to consider now the story with anomalies, etc. And so, which tells you that the renormalization of the mass, the corrections to the mass, have to be proportional to the mass itself. And already this tells you that this has to be a logarithmic correction, okay? But anyway, now you see what is happening in the case of supersymmetry. What is happening is that fermions, they have a protector. They have a very good protector, the chiral symmetry. But what supersymmetry does, it relates the scalars which were not protected before to the fermions which are protected. So scalars get sort of an induced protection. Okay? So this is what is happening. Now, we could have actually introduced supersymmetry from completely different perspective. Okay? We could have asked, can I have an extension of the space-time symmetries, okay, which is non-trivial? Now, as we know, in field theory, we have very important space-time symmetries, which are Lorentz invariance, okay, and translation and translation invariance symmetries, right? So we have the so-called Poincare group. And Poincare group, and we usually classify particles by representations of the Poincare group, meaning that we classify them by their masses and spins, right? And so, in particular, the shift of the coordinate by an arbitrary vector is a part of the symmetry of nature. This is a symmetry of nature, as far as we can tell. So the question is, can we extend the space-time symmetry of nature to something new and unbroken or exact without obtaining a triviality. Okay? And it turns out that there is a unique way of doing it, okay, which is extending these coordinates by introducing new coordinates which are fermionic and requiring a shift symmetry under these fermionic coordinates. So in other words, you see, we discussed these high-dimensional theories, right? So in high-dimensional theories, we said that we had four-dimensional space-time coordinates, and then we added an extra-dimensional coordinate, x5. Now, this high-dimensional theory, of course, it's an extension and a very dramatic extension of the space-time. But the coordinate that we introduced was the usual one. Okay, remember we had these two observers, Bob and Alice. They were normal people, and they used the same rulers. We could measure this x5 coordinate by exactly the same ruler. You take a normal ruler, you measure normal coordinates, and you measure x5 by the same ruler. In other words, the coordinates, they were bosonic numbers. Okay, they were usual numbers, bosonic numbers. The dramatic thing about supersymmetry is that the coordinate that you are introducing is not even a boson. Okay, it's not a usual number. It's a thing that anti-commutes. It's a fermion. Okay. Now, this is why sometimes people call supersymmetry a quantum dimension. Why? Because, you know, classically fermions are not really a well-defined object. Fermion nature, Pauli statistics, is something intrinsically quantum mechanical. So the moment you introduce a coordinate which you are saying you can measure, but this is something that you cannot write down in terms of normal number, but something that anti-commutes with itself, you are in a quantum mechanical territory. Okay? Anyway, so it turns out that if we think that our space-time has new dimensions, okay, new dimension, but this dimension is not bosonic, but is fermionic, then we end up with a unique extension of the space-time group, it turns out, and this gives us a supersymmetry. Now, let me explain why this should give us a supersymmetry, and then we finish this lecture, okay? The reason why this should give us a supersymmetry is pretty simple, okay? And qualitatively you can understand in the following way. Now, suppose I have this, let's visualize this, I have a coordinate x mu, which we live in those coordinates, right? And then there is a perpendicular coordinate theta alpha, okay? So in reality, now our space has more dimensions, except that those dimensions are fermionic. Otherwise, we're fine, okay? So now, let's say we have an observer, again, two observers. Let's introduce Alice, who lives in these dimensions, can only measure these coordinates, okay? So Alice is here, four-dimensional one. And Bob is somewhere here. And Bob lives in this superspace, okay? Now, for Bob, there are fields that are fields in superspace. Just like we had gravity, which was propagating in fifth dimension, right? So here we have a field which propagates in high-dimensional superspace, okay? So let's say we have a field, let's call it S, and this field obviously is a function of normal coordinates and the super coordinates, okay? Now, from the point of view, from Bob's point of view, this is just one superfield, okay? Some object which simply is a boson. On its own, let's choose the spin of this guy to be boson, okay? Of course, Bob can still measure spins and masses and everything. Poincare group is still unbroken. It's a full scale, it's a fully valid group. We can classify everything again with those representations. So this guy carries spin 0, so it's a boson, okay? Now, what this object represents from the point of view of Alice. Now, remember, Alice is somebody who cannot measure these coordinates theta, okay? So, from the point of view of Alice, the convenient way to study this field would be to take it, okay? Would be to take it and simply Fourier expanded or Taylor expanded, okay, in terms of this coordinate, okay, theta coordinate. So then there will be, the first term will be simply a function of x mu, okay. Then there will be a next term which will have first power of theta, okay, in front. And because the whole thing is a boson, it has spin 0, the coefficient of this will be a fermion. Then there will be somebody who will have 2 powers of theta, okay. So this will be again something, some kind of scalar. Then you can even have a vector, okay. You can make vector out of 2 fermionic things, and so on, okay. Now, the great thing about this expansion is that it will truncate after certain finite power. Why? Because if we introduce this theta to be a spinor, okay, let's introduce it to be a Majorana spinor, okay? So let's say I introduce a Majorana spinor with 4 components, real Majorana spinor with 4 components. There are only 4 numbers available. There is theta 1, theta 2, theta 3, theta 4. But because they anti-commute, the square of any given theta is 0, okay? Which means that your expansion will terminate maximum at 4 theta, okay? So having 4 thetas in a product is an absolute maximum you can have in any expansion of this type. Now we got to the point. So what do we got is the following thing, that from the point of view Alice cannot operate with these theta numbers. She cannot measure. She does not have a ruler to measure theta. But she has a ruler and everything to measure normal fields and normal coordinates. So she would tell you that actually this superfield is bunch of normal fields, except they come in same mass, but different spins. And there is a scalar, then there is a fermion, because these guys are functions of only x, right? There is a vector, and so on. And their number is finite. And they are related by, simply, their masses are related simply from the fact that they represent one and the same field in high-dimensional superspace, which is a definite representation of the Poincare group, meaning that that field carries a definite mass. Because Poincare group is still a very good group it's a still valid symmetry to classify representations, okay? So you see that immediately, from the point of view of Alice, she sees components of this bigger picture. And she thinks that there is a strange thing, that because there are these bosons and fermions, and strangely they are related, their masses and couplings are related. But in reality, what is happening is that these are fragments of the superfield, which lives in extra superspace, okay? So that's the way she arrives to supersymmetry. I think I should stop here and, okay, we continue. Okay, I'll see you at the discussion session now.